All right, so extended period simulations, or EPS, allows us to see what happens in our system over time. And what do I mean by over time? You can run this for 24 hours, 48 hours, for a whole week. Most of the time people run it for 24 hours up to 3 days because we see cyclical patterns, right? So maybe Monday through Friday, our wastewater usage is pretty identical from one day to the next, but maybe on the weekend it switches a little bit. So that's why typically you don't run it for more than a week. Mathematically, what this an EPS run is a series of linked steady state runs. This is not transient analysis. So if you're doing that kind of work, we have another product called Bentley Hammer. And this EPS is what we use in the SewerCAD solver. Okay, so everything I'm going to say in this presentation applies to that. So why would we be interested in looking at things changing over time? Well, the flow in a system doesn't remain steady because the loading variations due to domestic and industrial wastewater use, or water use that becomes wastewater. You could also have variations in inflow and infiltration during wet weather. Also, as we just learned, this lets us see how many times and when a pump turns on and off. If you have flow regulating devices or changes in tailwater levels, you can see how that affects your system as well. What can we see in an EPS run? We can see the wet wells filling and draining. We can see the pumps turning on and off. We can see how pressure changes, hydraulic grate line, flow rates, how they change during the day. We can see the effects of diurnal variation. We can see what happens the day that it rains. How does that affect the flows in our pipes? So the way this works is that the algorithm in SewerCAD generates hydrographs for the gravity portion, and then it routes those hydrographs to the wet well, and then it does the pressure calculations for the force main system, determines the levels in the wet wells over time, and then the hydraulic grate line is calculated for each of your time steps. Why? Because we know the wet well elevation, or what we call boundary conditions. And so that using those boundary conditions and the flows that we had, we can determine the hydraulic grate line using the backwater analysis. Okay, so you've already built your system in steady state, similar to what we did in this workshop. What else now am I going to require to turn this into an EPS? First thing is the temporal loading patterns. So before we were saying, okay, at this manhole, I'm going to enter, 100 gallons per minute, for example. That's too much, but whatever. X value at this manhole. But we weren't telling it if it happens all at once, or if it happens maybe nothing in the morning, and then all of a sudden, boom, we get 50, and then maybe at 6 p.m. we get another 20, or we haven't specified that, and we have to come up with that. And sometimes it isn't too easy to develop that, so you have to put a little bit of work into that. Also, we need to know at the beginning of the simulation what was the level inside the wet well and what is the cross section of that, and very precisely, because we need to know how the volume will change. You need to know how your pumps are controlled. So what are the triggers? If there are pipe controls, you need to know that as well. You need to determine how long you're going to run this for. So 24 hours, 48, 72, more. And what is your time step going to be? Typically an hour. So looking at the first thing, coming up with that diurnal flow, or what we call in the software a pattern. Here's an example of the components of a typical diurnal residential flow. So showers, washing machine, toilets, dishwasher. And of course, every day is different in every house, and you gotta come up with an aggregate pattern. So it isn't 100% precise, of course. It's just our assumption. Okay, so how can you define flow that changes in the program? You can input a hydrograph, which is a full flow versus time graph for each of your nodes. But that would require a lot of work to coming up with a full hydrograph. So what most people do instead is they set what we call an average flow, similar to what you would already have in your steady state, and then apply a unitless pattern to that average load. And how do you come up with that pattern? Typically, you look at the flow monitoring or the flow meter at the treatment plant. So you know what was the incoming flow every 15 minutes, every hour, or however intervals you have. And then you calculate, let's say, your 24-hour average flow. So for each time step, you'd say, okay, flow at time 1 divided by the average flow, and that gives you the multiplier for that time step. Okay, so that what you're left with at the end is a pattern multiplier per time of day. And you can make it look continuous or stepwise when you input it in SewerCAD. Okay, I say the treatment plant because it's something that most people would have, but if you have other measurements, maybe ideally you would want to have flow metering for your residential area and another for your commercial area or your industrial users and whatnot, but you got to do with what you have. So if you have one for those, then great, because that would help you come up with your commercial pattern separately from your residential and your industrial. Sometimes what we end up doing is that if there is a large user, like an industry, and if you have data particular to that user, then you can generate a pattern for that node and kind of separate it from the rest. But again, it all depends on what you have. Okay, so pattern, start time, and repetition, again, depends for how long you're going to run your model. So let's say you're going to run it for 3 days. Then you'd have to come up with a pattern for 3 days, or simply say, oh, it's my 24-hour pattern that repeats 3 times. So it's up to you. Again, depends on what data you have. Typically, we start at midnight, run it for 24 hours, which is actually what we're going to do in the example. Okay, so what options do I have for entering loads in an extended period simulation? If for sanitary loads, you have these 3 options: unit load, hydrograph, and base flow and pattern. Unit load, you guys used it yesterday. So how many customers per hotel, for example. In Hydrograph, you're actually entering flow. So if you have measured the flow, you would input it in a flow versus time. And pattern load is your base flow applied and a pattern that you apply to it. And typically for rain-derived inflow wet weather loading, you can either, if you have measured the flows, you can input a hydrograph. or you can also input a pattern load. Okay, so unit loads, you guys again used this yesterday. The new thing here would be that you have to create a pattern and associate it with the unit loads that have already been defined. If you're running this for 72 hours, let's say, your pattern has to be a multiply. The word's escaping me, but if you're running it for 3 days, then your pattern has to be at least 24 hours. It can't be a pattern of 50 hours because, then you would have to run it for 50 hours or 100 or 150, a multiple of that duration. Here's what a hydrograph would look like. And this kind of goes back to what we were talking about, what happens when you pour flow at a manhole, let's say. You may pour at this rate, the incoming one that you see, but if you go, I don't know, 10 meters downstream, and you look and you measure it there, you're going to see that the shape, the total volume has remained. So the total volume under these two graphs is the same, but the shape of the hydrogram has changed. And that's because of the attenuation we were talking about, right? So because it takes time to get there. So the farther you move, the more attenuation you're going to find. Okay, so the way mathematically this works is we solve the first time step, and then the results become the new initial conditions for the second time step. We run it, get the results. Those results become the initial settings for the third time step, and so on. Okay, so what is the time scale? It depends on what you're trying to simulate. Typically, for a large system, 1 hour time step is sufficient. Could be run for 24 to 72 hours. But if you're doing pressure sewers, those grinders that we talked about earlier, it could be a 2-hour simulation with a 10-minute time step. Do notice that when you go to the options in your calculations, you get to ask a hydraulic time step and a hydrologic time step, and also a reporting time step. So what is the difference between them? Well, the hydrologic is what is used for the routing. So remember we said we calculate the flows, we kind of generate this hydrograph, and then we route it through the system. That's a hydrologic time step. The hydraulic is what's used for velocity, hydraulic rate lines, kind of part of our profile. I don't know if you remember, guys, but when we did the first demo yesterday, these two hydrologic and hydraulic time steps were different. So at some point, our profiles would just kind of disappear. You wouldn't see the hydraulic rate line or the energy rate line. And it's because the hydraulic time step was much bigger than the hydrologic. So when in doubt, always set them to be the same. Might take a few more seconds to compute, but then you won't see any gaps. Again, the duration could be 24, 48, 72, or more. And typically, we run 1 hour hydraulic time steps, 0.1 hydrologic time steps. Okay, some basic things. The total duration must be a multiple of all time steps. The hydrologic has to be equal to the hydraulic, or it can be less. And then you get to set when you want to report all your results at every single point, which basically uses the lower of the hydrologic or hydraulic. Or you can say, no, I don't care. I just want to see what happens every 2 hours. Or variable. You can be very detail as to when you want to report them. There's something that we're going to get familiar with. It's called a time browser. Lets us browse through different times of the simulation, and here you can pick different increments, only the pressure, times, etc. Okay, wet wells. You notice when you input the data for the previous workshop that we had you enter the elevation. So elevation, everything, I kind of prefer always to use elevation rather than level, because sometimes, all these levels are in reference to the base elevation, but sometimes people forget, and this way, that if you've entered elevation of 170, that is in regards to all the elevations and all the nodes in your system. So I find elevation less prone to errors. So you have your base, your minimum level, your low alarm, initial, high alarm, and maximum. High and low alarms, you can set them so that if your simulation, if the wet well in your simulation ever reaches those alarm levels, there will be a warning generated. So you get a notification saying at time 2.15, the high alarm was reached. So you can be like, oh, I'm running this wet well pretty full, especially if you get it several times. But very important, the minimum and maximum, if your tank or your wet well ever exceeds those values, so it goes below the minimum or above the maximum, the tank would be disconnected, and you actually get error messages saying the tank is disconnected, the wet well is disconnected, some results are compromised. So just remember that. Okay, controls. We need to tell them what triggers things to go on and off, in particular pumps. It applies only to the pressures, and you can do a digital or analog setting. I'm just going to go through this. This is pretty simple, but it could be more complicated if you wanted to. There's a wizard when you set up the controls, which I'm going to stop here and just show you. I'm going to take this filter off for just a second. Okay, so as long as you're using the GVF solver, which again, most of the time you're going to want to be there, you can say, okay, pump P1 is controlled by wet well, pick the name of the wet well. It is turned on at this elevation. So when the pump is really full, let's call it 150 for now. And then once it has dropped the level to 140, turn it off. That's how simple it could be to set up your controls. However, if your controls are more complicated than that they involve times or flows or other things other than wet well levels, then you would want to set up conditions, actions, conditions, and then combine them in a control. That's what we're going to take a look at now. And again, this is like a really rare occurrence, but we cover it up anyway. So if you're using those controls, then basically sounds like this. If this happens, then do that. Or else do this other thing, right? So you create the actions, you create the conditions, and then you combine them. Here's an example. If the hydraulic rate line at the wet well is greater than 200, then turn the pump on, or else leave the pump off. Okay, here are some examples of conditions you could have. Hydraulic rate line at a node, time from the start, clock time. And here are some examples, things that you could have. Okay, so you can go to components controls to set this up, or simply go to the pump properties, go to controls, and use the control wizard. I highly recommend it if you're using controls based on tank level. All right, so we said how great this was, and really most of the time it just means coming up with those patterns for your loads, because you pretty much already had everything else, right? So if you're able to do that and run your EPS for however long you want, you get to use graphing, which is great because it shows you the values changing over time. You can see how your pump is cycling. You can see if the wet wells are overflowing. You can see if at any point your sewers are surcharged. You can see if you have enough capacity or not. You see if your manholes are ever flooded, or if your attractive stress target is not reached at some point in the simulation. And we use a lot of the color coding, network navigator. We'll use that in the workshop, so you'll get to see what that is like. Okay.
If you found this video helpful, please give it a like. If you want to see more such series, consider subscribing to our channel. Thank you, and see you next time.